Welcome to the Statistical Blueprint, where we demystify the core statistical concepts essential for truly understanding machine learning. Today, we're diving into fundamental probability distributions and descriptive statistics, uncovering how they directly influence our data insights, model assumptions, and even how we engineer features. Think of statistics not just as numbers, but as the language your data speaks, guiding every decision you make in ML. Our journey begins with descriptive statistics, starting with measures of central tendency, the mean, median, and mode. The mean, or average, gives us a quick snapshot of the typical value. The median, the middle value in a sorted dataset, is robust to outliers and offers a better sense of centrality for skewed data. The mode, the most frequent value, highlights common occurrences. These simple statistics are your first step in understanding where your data points tend to cluster. Beyond centrality, we need to understand data variability. This is where variance and standard deviation come in. Variance quantifies how spread out the data points are from the mean. Standard deviation, the square root of variance, provides this spread in the original units of the data, making it more interpretable. A small standard deviation means data points are close to the mean, while a large one indicates a wider spread. Grasping variability is crucial for assessing data reliability and range. Now, let's explore some key probability distributions, starting with arguably the most famous, the normal, or Gaussian, distribution. Characterized by its iconic bell shape, it's symmetrical, with its mean, median, and mode all coinciding. Many natural phenomena, from human height to measurement errors, approximate a normal distribution. In machine learning, it's foundational. The central limit theorem tells us that the distribution of sample means will approach a normal distribution, regardless of the original population distribution, a concept vital for hypothesis testing and confidence intervals. Consider an example of the normal distribution in action. Imagine plotting the SAT scores of all students in a large school district. You'd likely see a bell-shaped curve, with most scores clustered around the average, and fewer students scoring very high or very low. This visual pattern helps us understand the typical performance and the spread of abilities, directly informing how we might design educational interventions or predict future academic success. Next, we encounter the uniform distribution. Unlike the normal curve, a uniform distribution means every outcome within a given range has an equal probability of occurring. Think of rolling a fair six-sided die. Each number from 1 to 6 has a 1/6 chance of appearing. In machine learning, you might see uniform distributions in random sampling, or when initializing weights in a neural network where each weight is equally likely to take any value within a specific range. Moving to discrete distributions, we have the Bernoulli and binomial. The Bernoulli distribution models a single trial with only two possible outcomes, like a coin flip. The binomial distribution extends this to a fixed number of independent Bernoulli trials. For instance, if you flip a coin 10 times, the binomial distribution tells you the probability of getting exactly 7 heads. This is incredibly useful in classification problems, where we're often predicting success or failure. The Poisson distribution helps us model the number of events occurring in a fixed interval of time or space, given a known average rate. For example, it can predict the number of customers arriving at a store in an hour, or the number of typos on a page. It's particularly relevant when events are independent and rare, and it's a critical tool for understanding event frequencies in various real-world scenarios, from network traffic to defect rates. Beyond mean and standard deviation, measures like skewness and kurtosis give us a deeper understanding of a distribution's shape. Skewness tells us about the asymmetry of the distribution. Positive skew indicates a long tail to the right, while negative skew means a long tail to the left. Kurtosis measures the tailedness of the distribution, indicating how many outliers exist. High kurtosis means more outliers, while low kurtosis suggests fewer. These insights are crucial for robust data analysis. Understanding these distributions profoundly impacts our model assumptions. Many machine learning models, like linear regression, assume that the errors, or residuals, are normally distributed. Violating this assumption can lead to suboptimal model performance or incorrect statistical inferences. Knowing your data's distribution helps you choose appropriate models and validate their underlying assumptions for better results. Finally, statistical distributions are pivotal for effective feature engineering. If your data is heavily skewed, a log transformation or square root transformation can often normalize it, making it more suitable for models that prefer normally distributed inputs. Recognizing outliers, which often sit in the tails of distributions, allows us to decide whether to remove, transform, or cap them. These steps are not arbitrary. They are statistically informed decisions that directly enhance model performance. In conclusion, the statistical blueprint of your data, through descriptive statistics and probability distributions, is not just theoretical knowledge, it's a practical toolkit for every machine learning practitioner. It empowers you to interpret data patterns, select appropriate models, engineer robust features, and ultimately build more effective and reliable ML solutions. Embrace these statistical foundations, and you'll unlock deeper insights and more powerful predictive capabilities in your machine learning journey.